This is a question about lightning and thunderstorm, and a lot of details given in this question stem. The time, the lightning discharge, the distance, the current, the power, the temperature, and the speed of sound. So, and then also there's one more piece of info here, 2.5 kilometers. The mountain is 2.5 kilometers from the man. And so quite a lot of information here. We will attack this question point by point, okay, rather than trying to digest everything at one go. So the first question, for each lightning flash, every time there's a lightning flash, the man can hear a loud sound of thunder followed by a softer one. So they will always have two sounds. Why are there two sounds? So one sound very clearly has to be from the thunderstorm direct to the man. This will be the first sound. Where will the second sound come from? Second sound will have to come from the sound of the lightning, the sound of the thunder actually doesn't just go in one direction. It goes in many directions. And this is the direction we are looking at. So there's one that is going to go to the mountain, hit the mountain, and then it will have to bounce back and go towards the man. So this will cause the second sound. So the first is the direct sound of thunder. The second is the echo of the thunder from the mountain. So why is it that the second sound, which is the echo, has to be softer? So when it's softer, we are actually looking at the energy. So sound is a form of energy. Sound carries energy. And so we are looking at why the energy has decreased. So the energy has decreased from the first thunder to the for the first sound to the second one. So the second one, because it is an echo, some of the energy could have been lost, but where? So where is the echo? How can the echo be lost? How can the energy be lost? So we look at the situation again. Based on the diagram, it's easier for us to see. So for one thing, the lightning, the sound, after hitting the mountain, what could the mountain do? Okay, so the mountain, sound is a wave. So when it reaches the mountain, part of it could have been absorbed by the mountain in terms of causing some of the particles or even the whole mountain itself to vibrate a little bit. So it transfers the energy to the mountain. The other possibility is that because the surface of the mountain, as given in this diagram we see, is a bit rough, so it could also scatter the sound a bit. So it can transmit, it can reflect the sound in many different directions. And that will spread the sound energy out. Or we can also look at it this way. This first sound, this is a distance that is traveled. Along the way, sound energy could have been dissipated. Okay, and this distance is way longer than this. Okay, so now there's a longer distance in which sound energy could be dissipated, and that's where the sound could be dissipated through the surroundings, just by air, just because of the longer distance. So these are three possible reasons. I will just give you one. Okay, I've decided to give you two. So one is could be absorbed by the mountain surface. The other one is that, not most. So more sound energy could be dissipated to the surroundings due to the longer distance traveled by the echo compared to the direct sound. So the next question, the distance between the man and the man and the thunderstorm, if the time lapse between the two sounds is 4.4 seconds. So we know that the thunderstorm, this distance is unknown, but this is the first sound, and then we have the second sound, that is the distance traveled this way. This is the second sound. And so we know this distance has been given in the question. Mountain, which is 2.5 kilometers from the man. So we know this distance, and we know the time lapse, which is the difference in the time taken for the sound to travel. The sound took 4.4 seconds to travel this. And so with that, knowing the speed of the sound, I can actually calculate the distance. The distance here. And with this distance and this distance, I will then be able to calculate this distance, which is required by the question. So I'm going to call this distance between the thunderstorm and the mountain D1, and then this is a capital D, which is the distance between the man and the thunderstorm. So the sound took 4.4 seconds to travel this distance, so which means that it actually traveled 2D1 at the speed of 340 meters per second as given here. So I take it as the speed is equals to the distance over the time, and so I have 340 equals to 2 d1 over 4.4, and so d1 is equals to 340 multiplied by 2.2, 748 meters, and so now I can find big D will then just be 2.5 kilometers minus 748 meters, and that gives me 1750 meters, and this is to 3SF. So all our answers leave it to 3 significant figures. So now we're looking at when the distance between the cloud and the ground is 400 meters, what is the amount of charge that flows through during discharging? Let's try and extract information from this place where we tried to see, we already read through just now. And so very quickly, when the distance between the cloud and the ground is 400 meters. So all these data that were given actually apply, and so I can use this. So the average time for discharge is this, 4 times 10 to the power minus 3 seconds, and the amount of current is this. So how is current, I, and time, T, related to what the question wants, which is the charge, Q? How are these 3 quantities related? So Q is actually IT. Or if you want, you can write that current is actually equals to charge over time. So I can actually put them together. And what are all the quantities that I have? This is what I want to find. So this is my unknown. I already have what is my current and what is my time. So go back to the question. Current is 20,000 ampere. And then I have time, which is 4 times 10 to the power of minus 3 seconds. And if I multiply them together, I get the total charge Q will now be equals to AT. And what is the unit for charge? It is Coulomb. So it's a capital C. So this is my answer, 80 Coulomb. So what is the typical potential difference between the cloud and the ground? So coming back, I have the charge, and now if I want to find the potential difference V, how are these two related? I'm still short of a small quantity, and what is that quantity? That quantity is actually work done, or actually energy. So I'm really looking at energy over here. So how do I get energy? The next closest I can get is power produced in every channel of the flash is this. Okay, so now we want to look at this as the power per meter of the channel. So how long is that channel? What is this channel that we are looking at here? And so this channel is actually the lightning discharge channel. And what is the discharge channel? The length of the discharge channel is really just this height. The height of the cloud above the village, above the ground, and it's actually given right at the start here, 400 meters. So this is the height, 400 meters, and this is the lightning stroke is a discharge channel. So this is the power per meter of the channel. So now I know the channel is 400 meters, so I know the power. But that's still the power. How do I get from the power to the energy? I again need to go back to the time that is taken. So these are the quantities that I will need to solve this question. So let me write that first. The potential difference will be equals to the work done to drive a unit charge per unit charge. Okay, so Q, and now I already have Q earlier, so now I need to look at solving for work done. And so I will write that work done is actually power times time. And here my power is the power dissipated per meter of the discharge path. I need to multiply by 400 meters. So this is the length of the discharge path. And this is my power multiplied by the time that we were given right earlier on as well, the same value that we have used, 4 times 10 to the power of minus 3. And I have the work done, 1.6 times 10 to the power of 8 joules. And so I substitute it into the equation above, 1.6 times 10 to the power of 8 over our answer earlier, which is 80, and I have my final answer, 2 times 10 to the power of 6. And the unit is going to be volt. So that's the potential difference that I'm looking at here. So the energy involved in the discharge, we have actually found it earlier. That is fine, which is over here, the energy involved in the discharge. And so you can just make use of this working in the next part. And so your answer, 1.6 times 10 to the power of 8 joules. So that's the answer.